Let's dive deep into logistic regression, a powerful algorithm for classification problems. Logistic regression is a classification algorithm that separates data into distinct categories using a decision boundary. Let's start by understanding what logistic regression actually is and how it differs from linear regression. Logistic regression is a supervised learning algorithm primarily used for binary classification tasks, predicting one of two possible outcomes. Unlike linear regression, which predicts continuous values, logistic regression predicts the probability that an instance belongs to a particular class. It uses the logistic function, also called the sigmoid function, to map any real-valued number into a probability between 0 and 1. This is the sigmoid curve, which smoothly maps any input value to a probability between 0 and 1, with 0.5 as the decision threshold. The sigmoid function is the mathematical heart of logistic regression. The sigmoid function is defined as sigma of z equals 1 divided by 1 plus e to the negative z. The sigmoid function has several important properties that make it perfect for classification. First, its output is always between 0 and 1, making it interpretable as a probability. When z equals 0, the sigmoid outputs exactly 0.5, serving as our natural decision boundary. As z approaches positive infinity, the sigmoid approaches 1. And as z approaches negative infinity, the sigmoid approaches 0. These three key points on the sigmoid curve show how it transitions smoothly from low to high probabilities. In logistic regression, we combine linear regression with the sigmoid function. Our hypothesis function h theta of x equals the sigmoid of theta transpose x, where z equals theta 0 plus theta 1 times x1 plus theta 2 times x2, and so on for all features. Substituting into the sigmoid, we get our complete hypothesis function for logistic regression. The flow is simple. We take our weighted input features, pass them through the sigmoid function, and get a probability output. The decision boundary is where our model decides between the two classes. We predict class 1 when our hypothesis function outputs a probability greater than 0.5. That is, predict y equals 1 if h theta of x is greater than or equal to 0.5. And predict y equals 0 if h theta of x is less than 0.5. Since the sigmoid equals 0.5 when its input is 0, we predict class 1 when theta transpose x is greater than or equal to 0. Here we see a linear decision boundary separating two classes of data points, with yellow dots on one side and blue dots on the other. To train our model, we need a cost function that measures how well our predictions match the actual labels. We cannot use the squared error cost function from linear regression because it would create a non-convex optimization problem with many local minima. Instead, we use the log loss or cross-entropy cost function, which is convex and has a unique global minimum. This cost function has two important properties that make it ideal for logistic regression. When the actual label y equals 1, the cost is negative log of our predicted probability. When y equals 0, the cost is negative log of 1 minus our predicted probability. These curves show that the cost increases dramatically when our prediction is wrong, penalizing confident but incorrect predictions heavily. We use gradient descent to minimize the cost function and find the optimal parameters. The gradient descent update rule is theta j gets theta j minus alpha times the partial derivative of the cost function. The gradient is computed as 1 over m times the sum of prediction errors multiplied by the feature values. Gradient descent iteratively updates parameters, moving down the cost function surface until reaching the minimum. Once trained, we use our model to make predictions on new data. First, we compute the weighted sum of input features using our learned parameters. For example, z equals theta 0 plus theta 1 times x1 plus theta 2 times x2. Next, we apply the sigmoid function to convert this into a probability. This gives us the probability that y equals 1 given input x. Finally, we apply a threshold, typically 0.5, to get our binary class prediction. The complete prediction pipeline. Input features to weighted sum to probability to final class prediction. Let's review the key concepts of logistic regression. Logistic regression uses the sigmoid function to map any input to probabilities between 0 and 1. It optimizes parameters using gradient descent to minimize the log-loss cost function. The model creates linear decision boundaries that separate different classes in the feature space. Despite its simplicity, logistic regression remains a powerful and widely used algorithm for binary classification problems.